Homomorphic encryption, the trust-free black box. Homomorphic encryption is, at its core, a cryptographic technique that allows computations to be performed directly on encrypted data without decrypting it first. Think of it as a black box. You put data in, encrypted. A server performs an operation on the data inside the box, and what comes out is still encrypted. When you finally take the output, decrypt it, and look at the result, it's the same result you would have gotten if you would have decrypted the original data, done the computation, and then re-encrypted the result. This fundamentally inverts the traditional security model. Usually, to process data, you must decrypt it, exposing it to the processing entity, e.g., the cloud server. That means you have to trust the entity not to look at your data. Homomorphic encryption removes that trust requirement. As a security professional, this is a paradigm shift. This shifts the security boundary from trusting the service provider to trusting in the mathematics of the encryption scheme. The data remains protected even from the system running the computation. The homomorphic computer. Conceptual. A computer capable of running such an underlying system wouldn't be a revolutionary hardware concept in the way a quantum computer is, but rather a system optimized for computation on ciphertext. Specialized hardware. Future. Right now, homomorphic operations are very slow, orders of magnitude slower than operations on plain text. A homomorphic computer would likely involve specialized coprocessors, like ASICs or FPGAs, designed to accelerate the polynomial and ring arithmetic that underlies most practical homomorphic encryption schemes, like BGV, BFV, or CKKS. This hardware would essentially be optimized for noise management and modular arithmetic on large numbers. Specialized software stack. More immediately, it's about a highly optimized software stack, compilers, libraries, and virtual machines, specifically designed to translate standard computing tasks, e.g., find the average, train this model, into the series of necessary homomorphic operations, like homomorphic addition and multiplication. The security ramification. This computer is a utility provider, not a trusted agent. It can do work for you, compute, but it cannot gain knowledge from the work it does. Ramifications. A security game changer. The ramifications of widespread, fast, homomorphic encryption are profound and, frankly, a bit unsettling for those of us who focus on traditional defense. Privacy-preserving cloud computing. This is the most obvious benefit. You can upload your data, medical records, financial portfolio, proprietary algorithms to the public cloud, and the cloud can process it without ever knowing what the data is. The server becomes a blind tool. Encrypted biometrics, database queries. A police department could query an encrypted fingerprint database to see if a suspect's print is a match, and the database owner, or the police, never has to reveal the full database or the suspect's print in the clear. You get the answer without the data exposure. Zero trust machine learning, private AI. Companies could train a machine learning model on sensitive encrypted user data. The model benefits from the data's patterns, but no human or system ever sees the individual inputs. The knowledge is extracted, but the privacy is maintained. The surveillance state's dilemma. Widespread, fast homomorphic encryption makes mass data interception, like bulk wiretapping, much less useful. The adversary, government, criminal, or corporate spy, captures ciphertext, but if they cannot decrypt it, and the computation is still done on the server, they are left with garbage. It is a huge boost for individual autonomy in the digital space. A new vulnerability surfaced. However, the complexity of homomorphic schemes introduced new vulnerabilities. A small error in the implementation of the underlying mathematics, or poor noise management, a critical component where operations add noise that must be managed to prevent decryption failure, could render the entire system insecure. Complexity is the enemy of security. We're trading trust for mathematical complexity, and we must audit that math ruthlessly